Hey everyone, so in this video we're looking at function notation. In the learn by example we had the definition of a function is for every input there's only one output, or for each x there's only one y value associated with that. Here I'm going to pick up with domain and range of a function and then spend most of my time looking at function notation and how to use it. We'll only see it a little bit in this class, but as you go on to future classes, like by the time you get to calculus, almost everything is phrased in terms of function notation, so it really does become kind of the dominant notation that you'll see later in math. For domain and range, remember that domain is our x values and range is our y values. And dependent on how the information is given, that determines sort of how we write the solution set for that. Here where we have finite points, or I think on the learn by example there's also some problems where it was a table, we would want to make a list, and so for that we would say our domain is equal to, and then we use a brace to indicate that we're making a list, so we would write just out a list separated by commas. When it's something continuous like this next example, for that we would want to use interval notation. So our domain in this case is going to be all of the x values that are represented. So -10, -3, -1, 0, and 4. And that's all of the x's. And then for our range, and notice I'm working from left to right. I think on the homework it doesn't have to, you can write them in any order, but it is more proper to write them from lowest to highest for sure. And then from the range, I'm going to go from the lowest value again to the highest value, but this time we're thinking vertically instead of horizontally. So that's going to be, our lowest value is going to be -9, and then it's going to go to -5 and -4, and then to 2 and to 5. And that would be it. That's our domain and range for this particular problem. Graphs, they're a little harder, or people have a little more difficulty with them. So when we're thinking of a graph, it can help to think of it as projected down on the x-axis or projected onto the y-axis. So from here, our farthest point left is going to be at -1 right there. And then I have graph all the way up to, but not including that 2. So it's that segment that I want to indicate for my domain, because that's everywhere I have x's. So here we'll say the domain starts at -1, and I want to use a bracket because of the solid dot, so that would be included. And then that's going to go up to but not include the +2, because that's the x values. The y values, let me get rid of that, are going to be our range. And for that we want to go, instead of left to right, we want to go the lowest point on the graph to the highest point. So the lowest this graph goes is 0. And be careful not to mix that up with the 2, because now we're talking about y values, not x values. So 0 would be the lowest it goes. The highest it goes is 4, and it does include 4, because if I ask when x is 0, what's y, you would tell me it's 4. And so that's going to be a solid dot up there. And so from 0, not inclusive because of the open dot on the endpoint, up to and including 4. And that would be our range for that function. And then the rest of this we're going to spend working with function notation and either evaluating equations or solving equations. So this one we're given a graph, and for f of 3, that's replacing the x in the equation. And so that what that means is that for f of 3, we're being told x equals 3, and then we're being asked what does y equal in that case. So when it's in the parentheses, it's replacing the x, so that means we know our input and we're trying to get our output. So in this case, when x is 3, the y is going to be 2. When they give us f of x equals 3, f of x is like our y. So f of x equals 3 means that y equals 3 what x would make that be true. Scroll this up a bit so you can see it better. And so if we look over here where the y's are 3, that's right there. And so the x that would make that happen is 4. So we have to put in a 4 to get out y equals 3. So when the number is replacing the x, that means we know x, we're solving for y. When it's f of x equals something, you can think of that f of x as y equals, because it's going to be the y side of the equation, the function of x. So it's like our old y equals 3, and it's asking what value would make that true. And that's going to hold true for all the problems that we're working with in terms of function notation. So this next one we're given an equation rather than a graph. So I'm asked to find f of -3 first. So again, that's our x. And so we would substitute that in for x. And that would be -21 plus 4. So -21 plus 4 looks like that would be -17. So when x is -3, we put in -3, we get out -17. For part B of this one, it's saying f of x equals -10. So for that, it's asking us to solve for what value of x makes this equation come out to -10. If you think of this as just a plain old substitution, since f of x equals -10, we're putting that in this side and we're solving for x. So we do that, we'd have -10 equals 7x plus 4. Subtract the 4 over and get -14 equals 7x. Divide both sides by 7, and -2 equals x. So if I plug in -2 into this equation, that's the value that gets me an output of -10. And again, this is going to hold for everything. Replace x, that means it's x. When we have f of x equals, that means we know y. I think the rest of these are all evaluating at x's, yep. And it's just kind of, again, getting used to the notation of what it's asking. So if this said find, p of 5, we would plug a 5 in for all of those t's and solve. So it doesn't matter what is in the parentheses, that's what's going to go in for x. So if we're supposed to find p of t plus 1, that means that t plus 1 is going in everywhere there's a t. So that's going to look like 7 t plus 1 squared, so there I am substituting for the t within the squared, plus 6 t plus 1 minus 4. And now I just have some algebra to do to get this thing simplified. So 7. Ideally, remember in the earlier chapter on polynomials where we had the formula for foiling this out, and it should come out, we would do t times t for t squared, t times 1 and double it for 2t, and then 1 times 1 would make 1 squared. That said, usually people aren't great at doing that at this stage, so let's write them side by side and we'll do out the steps and make sure that we get there. The important thing is not to forget, and this is a pretty common error, and end up with t squared plus 1. T plus 1 quantity squared does not make that. It is a FOIL, and so we want to be careful to make sure we get those cross terms represented. Go ahead and distribute here and get 6t plus 6. Make sure we get all the way through the parentheses with that, and minus 4. So this is going to be 7. T times t will be t squared. On the outside I would get a t times 1, so that would be a plus t. On the inside I get another t times 1, so that's another plus t. So plus t will make plus 2t when I combine those. And then 1 times 1 will make 1. And then this is 6t. And we'll go ahead and combine those. So 6 minus 4 would be a plus 2 right there. And now I'll go ahead and distribute that 7 through. So 7t squared, 7 times 2 for 14t, and 7 times 1 for 7, plus 6t plus 2. 7t squared, 14 plus 6, that would give us 20t. 7 and 2 would make 9. And then I collected all my like terms, so that is as simple as I can make that. Happily, these next two, parts B and C, are way easier. If I'm finding P of negative t, that just means everywhere there's a t, I plug in a negative t. I just evaluate it for the negative. That ends up being a symmetry test in later math classes. So this is going to be negative t quantity squared, 6 times negative t, and minus 4. Scroll that up. So, 7, negative t quantity squared would be negative t, so that makes it t squared right there, minus 6t, and then minus 4. And that's it. And the last one is find p of k. So p of k is like literally just a variable change. All you're doing is putting k's any place there are t's. So that'd just be 7k squared minus 6k and minus 4. So just that simple, nothing else to do with it. Let's see, evaluate this function at 4b. So that means any place there's an x, that x is now going to be a 4b. And I just have to clean up and simplify after I plug that in. So f of 4b will look like 3 and then 4b squared plus 3 times 4b plus 2. 4b times 4b would be 16b squared. Careful to get the 4 squared along with the b. 3 times 4 give us a 12b right there, plus 2. And then just cleaning up that last bit a little bit, we'd go 3 times 16 is 48b squared, plus 12b, and plus 2. So all the math, we really already know how to do that. The only thing really new in this section is the notation and understanding what it wants us to do. And then this last example, we're evaluating this function at 3y squared. So that just means everywhere there's an x is now going to be a 3y. So f of 3y squared equals 4 3y squared cubed plus 4 3y squared plus 5. So cleaning this up, we'll have 3 cubed is going to be 27. Y squared cubed, so that's y squared, y squared, y squared, so that's y to the 6th. And remember from the exponent chapter, when we raise to a power, we multiply our exponents, so y to the 6th. And then 4 times 3 would give us a 12y squared plus 5. And last thing is just to clean up the 4 times the 27. So that would be 108 y to the 6th plus 12y squared and plus 5. And that would wrap up 6.1.